Hello, everyone. Welcome to the Bread of Life channel. I'm here with Leo from the channel Leophilius. You can find his channel linked in the description. He has some really interesting discussions on his channel with philosophy and science. And we are going to have a discussion about the Big Bang today. And I think Leo is hoping to help me understand and to believe in the Big Bang. And I'm hoping that I am going to make some of you guys skeptical about the Big Bang if it's currently a belief that you hold. I hope to show you that it is really an absolutely absurd modern myth that no grown up should believe. So, Leo, do you want to say anything to start?
Um, I mean, I would say, I guess nothing other than that the Big Bang or the hot Big Bang model is merely one aspect of what's often just referred to as LCDM amongst professional cosmologists, or just a concordance model, which is the lambda cold dark matter, which is where the CDM comes from, the lambda CDM or lambda cold dark matter model, which is the current model of cosmology. You aren't going to find at least an honest and respected cosmologist alive today who would tell you that this model is complete or even close to being complete. There are still a lot of things that we don't know. We're humans. Our technology has only come so far, and we have the capability to look only so far out and only so far back, and only so far down with respect to scale. We don't have all the answers. We don't know everything, but there are things that we do know with a very high degree of confidence, and there are things that aren't known with as high a degree of confidence, but are certainly strongly indicated by the data that we currently have at hand. And the idea that the universe was very, very early in its history in a very hot and very dense state from which it evolved is the conclusion that is corroborated by all of the available data that we currently have about the evolution of our universe.
Okay, well, let me just start by asking you this question. So, most people have heard this idea about Santa Claus that,
Mm-hmm.
a guy goes around and he's got toys in his sleigh enough for the entire for all the children of the world, right? Now, what do you think about the idea that Santa could fit in his sleigh toys enough for all the children in the world?
Well, because of what I understand a sleigh to be, and because of the amount of children I know exist in the world, I would just say that the concept seems um, just something that at least like nomologically is not something I would ever expect to manifest in reality.
Okay. What about if I said I could fit everything necessary for planet Earth in my purse?
When you say everything necessary for planet Earth, do you mean like all of the material composition of the planet,
Whatever's
or?
necessary, whatever would be needed for planet Earth to exist, I could fit the contents of that in my purse.
Well, I mean, technically speaking, yes, because I mean that's like all the elements that make up the Earth. Like I mean, the question is an interesting question, but there's also that there's processes that are involved in the formation of the Earth, and you can't like put a process in it like that. That's not how a process works. Like if you imagine flushing a toilet, I can't hold flushing a toilet in my hand. I mean, if my hand's big enough, I could hold a toilet in my hand, but I can't hold. I can hold a flushing toilet in my hand, but I can't hold the process of flushing a toilet just on its own in my hand. So in the same way, there are processes to the formation of the Earth that you're not going to be able to put in a container. But with respect to like the material composition of the Earth, yeah, you could fit it into the size into something the size of that bag. You could fit it into something even smaller than that.
And how about our sun?
Oh yeah.
So
Mm-hmm.
this big ball of fire that has enough energy to
Not
warm
fire.
our entire planet, well, of hot burning
Plasma.
gases, okay, that
They're not
are
burning.
enough to build, okay, whatever this is in the sky, which is warming
It's a
our
ball of
planet.
plasma that is undergoing nuclear processes.
I could fit what is necessary for that in my purse.
Yes.
And not only that, but billions upon billions
Mm-hmm.
of stars like that. and galaxies upon
Mhm.
galaxies all in my purse.
That amount of energy? Yeah, absolutely.
Everything in this universe, all the planets, all the galaxies, all the stars could fit in my purse.
Yeah.
Okay, is anybody else wake up? I really hope I'm waking you up. If you don't think Santa's toys or his sleigh is big enough to fit toys for children all around the world, why do you believe
But what is a
that
toy?
billions upon billions of stars and galaxies fit in this purse? Really? This is
Because
the dumbest thing that grown-ups
no,
have been
we do it all the
believed.
time.
Now, I often hear this idea that extraordinary claims require extraordinary evidence.
Mhm.
Would you agree with me that, Leo, this is an incredibly extraordinary claim?
No,
That
according to
all
modern
the
physics, no.
matter, all the matter in the universe, everything necessary to build everything in this universe could actually fit in this word. This is
Well,
an
it's not
extraordinary
just
claim.
that
So
everything
I
to
hope
build the universe, it's that the universe was at one time orders of magnitude smaller than your purse. In fact, so small that the concept of putting it in something wouldn't even make, I mean, it still doesn't. I don't know what it means to put the universe in something. But yeah, there was a point where space-time was that small and everything would thereby be that compacted.
Okay. So now let me ask you this. What physical process, what law of physics allows for the substance of the entire universe to start
General
out as a
relativity.
singularity?
Well, singularities aren't physical objects. That's a thing that we need to remember. But general relativity.
Okay, so you're saying, okay, and does general relativity comport with our what we know of quantum mechanics in a way that allows for the universe to begin as a singularity?
Yes, we don't understand that though.
Well, if you don't understand it, how do you know?
Well, because that's how it would have to be for how we know how the universe evolved.
Okay, Leo, this sounds a bit circular to me, right? You don't know, but you're already assuming that this
Yes,
happened.
we can infer based off of what we can see around us. And we
Okay.
know that the universe was extraordinarily small. We know that it underwent an inflationary epoch. And we know that we're going to need physics beyond general relativity to describe that. The fact that we don't yet have that physics doesn't mean that the period where we need that physics doesn't exist.
Okay, so you believe it exists.
Believe what exists?
You believe that the general relativity will somehow comport
No.
with what
General
is
relativity will be
Okay.
superseded by a better theory that describes space-time at significantly higher energies than what general relativity is currently capable of describing.
Okay, but right now, you don't have the physics to describe the universe beginning as a singularity.
Well, the universe didn't begin as a singularity. We don't even know if the universe began.
Okay, but I'm saying the story that the model tells.
That the
about
idea that the
singularity.
universe was in a
This
very
cannot
hot,
be
very
described
dense state.
Earlier you said we don't know. Okay, so I just want to establish that. And if you've changed your answer, that's fine. But we don't know what physics would allow for this to happen.
Well, I mean, we know what physics will allow for it. We don't know how to really like put that together into a solid theory that gives us good explanations.
Okay. So this is something you believe, and obviously you believe it based on evidence. So again, this is an extraordinary claim. I think it needs extraordinary evidence, and I'm ready to hear that. What is the evidence that supports this model?
The whole of the standard model of cosmology, or just like the specifically the hot Big Bang.
The lambda CDM.
Well, I mean, if you want, we can go through my the slides that I have, because that pretty much summarizes. I mean, it might take us like 10 minutes to go through it, but if you want all of the evidence, that would be the best way to do it, I guess.
Okay, sure. Yep.
So we have the lambda CDM model. It's an incomplete model. There's a lot that we don't. I mean, we don't even fully understand how galaxies form. We don't know how supermassive black holes formed, or at least got that large. I mean, we have idea. We know how black holes form, but we don't know how they would have gotten that large. There's a lot of things that we don't really understand because, again, we're humans and our technology has only come so far. And I think it's pretty obvious that as our technology improves, our understanding improves, as we can see with the James Webb Space Telescope, which is revealing a lot of things and allowing us to be able to correct our models to more accurately describe the reality around us, because that's how science works. It doesn't necessarily claim to have the final answers about everything and then work from there. It works from what we know and what we understand and tries to do its best to develop explanations and models that help us describe and understand the reality around us. So there's really two, maybe three fundamental aspects to contemporary cosmology. You've got inflationary theory, you've got the hot Big Bang model, and then some people might say that you've got dark matter and dark energy, but those are areas that are still very much being developed, but they are important. They are important with respect to the large picture here. So starting with the hot Big Bang model, this is where cosmology really started with respect to how we understand and how we look at the universe today. And this would have been started in the early 20th century, the 1910s, the 1920s. That's when we were really starting to get a much more accurate picture of the universe around us. And Einstein's general theory of relativity was one of the first ways that we knew that our previous picture of cosmology was likely incorrect. So general relativity is our theory of space-time. It tells us how things act in space-time and how space-time as a dynamic manifold, how it contorts, I guess you could say, as it interacts with mass energy present inside of it. And that interaction is what we understand as gravity. And Alexander Friedmann provided solutions to general relativity, to the equations, Einstein's field equations, and what his solutions were for. They were solutions to the equations, solving for a universe that is near homogeneously filled with matter and radiation, like ours is. And what was an intrinsic result of these solutions was that space-time cannot be static. That is, it can't just be there. It either has to be expanding or it has to be contracting, but it can't just be still. It cannot be static. Well, Einstein didn't like this. And so he actually added what's called the fudge factor, you may have heard of it, to these equations. It's known as the cosmological constant, and we actually still use it today. And they thought that the universe would have been contracting as a result of all of the gravity of everything inside of it kind of pulling and tugging on space-time. Space-time would slowly contract under all of that. And so what Einstein did is he introduced a factor into his equations that gave a repulsive force that perfectly canceled out this contraction of space-time, which would have kept space-time in a static state, because that's what Einstein and that's what most cosmologists believed. It wasn't until, I think it was actually originally in like 1923 that that galactic redshift was first observed. And I can't remember the name of the person, because I don't think it was Hubble that first observed it. I think it was Hubble that first observed and really defined what it was. So I guess I'll just jump to him. In 1927 through 1929, he was observing galaxies, and he observed an interesting feature that can be observed by any radio telescope of sufficient power. And that is that when we look at the emission spectra of distant galaxies, there's a red shift. There's a shift to lower energy levels on the electromagnetic spectrum than what we would otherwise expect, and that this red shift, is directly mathematically proportional to the distance away from us that these galaxies are. The further away the galaxies are, proportionately, the greater the shift, the red shift of their emission spectra. So what this means is that it isn't these galaxies that are physically moving away from us. It's the distance between us and the galaxies is growing exponentially. Well, not really exponentially, but I mean, in a more metrically, I guess is the right way to put it. It's a metric expansion of the scale in space-time that is observable at very, very large distances. And this is what confirmed that space-time is not static. It is, in fact, expanding, which is thoroughly in line with the solutions to Einstein's field equations that give a universe that looks like ours, one that is near uniformly and homogeneously filled with matter and radiation. So this is where Einstein called this cosmological constant, this fudge factor that he put in his equations, the biggest blunder of his career, because he should have just listened to what his equations were telling him when they said that space-time is not a static entity. It's either expanding or it's contracting. And here we have direct observational evidence that the universe is indeed expanding, and this fits perfectly with the prediction of the Friedmann solutions of general relativity. So we've already got two really good pieces of evidence here, and two things that we would expect to see if it were the case that the universe very early in its history was in a very hot and very dense state. But that's not all. We also have what was, I can't remember who it was. Somebody in the chat's going to know. I'm not looking right now because I'm looking at the slide. But they called it the smoking gun of the Big Bang. And that is the cosmic microwave background. This was observed in 1965 by Robert Wilson and Arno Penzias, and it was discovered accidentally. They were, I can't remember exactly what kind of survey they were doing, but I know they were doing some sort of astronomical survey. I don't know if it was stars or galaxies or what it was, but they were doing some sort of astronomical survey, and they kept getting this sort of you could call it almost like a hum in the background of their observations. And it was exactly the same no matter where they pointed their telescopes. And so they thought, okay, there's some sort of interference. So they recalibrated all their machines and everything. They cleaned the telescopes off because they thought it could be, bird poop or something like that even, that's causing some sort of interference. They did everything they needed to, and they continued to detect it. Everywhere they looked in the sky, and it was exactly the same. A very low energy background of electromagnetic radiation that's permeating all of space-time. And this very entity, the cosmic microwave background, has been extensively measured by humans. We've had the COBE, the WMAP, and the Planck satellites up there, all of which have measured it and mapped it to ever greater accuracy. And it is exactly what was predicted by the hot Big Bang model that was initially proposed by a Catholic priest by the name of Georges Lemaitre. So, and that was that if his idea was correct, that, well, the universe is expanding, which means that if we were to sort of like rewind the clock, so to speak, the universe would contract inward, and that at some point, taking Einstein's general theory of relativity as we understand it, the universe would very early in its history would have been in a singularity, a point of infinite density and infinitely small volume. And what's predicted from this, as we began to understand particle physics better and the particle physics involved in the early universe, how does particle physics and quantum mechanics and all that stuff work when you're dealing with very high energies like you would be in the very early universe? And what was discovered, and I'm going to come back to this slide, but what was discovered is that there would have been what's now called Big Bang or primordial nucleosynthesis is something that would have occurred if the universe were in a very hot and very dense state very early in its history. Then what this means is that as the universe expanded, and it has been expanding on the average throughout its history since that point, what we would expect is that as it expanded, this is going to cause the density of mass energy in the universe to slowly drop. The universe is going to effectively cool under its expansion. And at some point, you're going to reach a critical cooling point where you lose some of the energy that's there. It starts to dissipate a little bit more, and stable atoms are going to be able to form. Prior to this point, it would have been too energetic for stable atoms to form, which is a state that we know can exist, and it's what stars are made of. It's called plasma. That would have just effectively been plasma filling the universe. And electromagnetic radiation cannot travel through plasma, if it's a simplistic way of putting it, but it brings the point home. Electromagnetic radiation can't really travel in plasma. It's scattered off of the electrons and some of the protons, or I think more appropriately, some of the quarks that make up the protons, in this very high energy state. But as this state cools, those stable atoms will begin to form. The electrons will be able to be bound to the protons to form stable neutral atoms, with most of that being hydrogen, one proton and one electron. And that's largely what we see. Hydrogen constitutes about, I think it's about 70% today of the mass energy, the baryonic mass energy density of the universe. And was closer to about 75% back in the very early universe during the period of recombination, which is what this period is called, when stable neutral atoms formed. And what resulted from this formation of these atoms is that the electromagnetic radiation, the light, was now capable of traveling without being scattered off of all the electrons and the protons, because they're in the form of these atoms. And so there would have been a release of the electromagnetic radiation that would have traveled, permeated throughout all of space-time. And we should, if this model is correct, then we should be able to detect that electromagnetic radiation today. And we have. And we've, like I said earlier, measured it to ever greater accuracy with the COBE, WMAP, and Planck satellites. And that is the cosmic microwave background. This is effective proof that the universe was in a very, very hot and very, very dense state very early in its history, as is the abundance of light elements that are themselves a result of the same event, the recombination of matter, which allowed for the release of the electromagnetic radiation that we can detect and have measured very well today. And this would have created an abundance of hydrogen and helium, the two lightest elements on the periodic table. They should constitute most of the baryonic mass energy density in the universe even today, and they do. So this effectively confirms the hot Big Bang model. So I think we can pause here before going on to inflationary cosmology, if you have any questions, or if there's any questions from the chat that you would like to entertain. You're muted, Rebecca.
Sorry. Okay, now what effectively proves this? Or what did you say?
The cosmic microwave background effectively proves that the universe.
Let me get this straight. Okay, let me get this straight. We see some radiation in, the background of the universe.
That's everywhere. Everywhere in space.
Everywhere. We see radiation.
It's homogeneous. It's homogeneous to 1 part in 100,000.
Okay, wait. Because we see radiation, I'm supposed to believe that billions upon billions of stars and galaxies once fit in this purse.
Well, no, because your purse didn't exist.
Well,
there was too high energy for your purse. You do realize? You do realize?
I'm using it. Obviously, I'm using it, and actually, it's in a space smaller than this purse. I'll say it more clearly. Then, in a space existed. In a space smaller than this person.
Well, that's not really the right way to look at it. It's not. It's that space-time was compactified. I mean, that's.
So everything necessary, whatever it was that was necessary to build billions upon billions of stars, galaxies, planets, all fit in the space smaller than my purse.
Well,
you want me to
not really. There's a problem here. The problem is you keep explaining this in language that seems more an attempt to make the idea sound absurd rather than meaningfully represent what the idea is.
Okay, can you represent?
When you say it's like when Kent Hovind says, "Oh, well, you think that all the planets and the stars and the galaxies fit inside a space smaller than a period, the little dot at the end of a sentence." This is just a way of making an idea sound absurd, and I have to be honest, I think it's because you don't understand it.
How am I mischaracterizing it?
You do realize that when we collide particles at the LHC, that we're putting more energy into a smaller space than the planet Earth fitting inside your purse?
Okay.
But we've done this in experiments. This isn't hard for us to do.
But can you characterize it then? Okay, in a way that's accurate.
I think I did. Okay. Very early in the universe's history, at least with respect to how we can measure the universe and time and all that stuff, the universe was in a very, very dense and very, very hot state. Yes, everything was compactified. How dense? Well, what is it like about? Then I don't know what you're asking for, because I would characterize that
smaller than this purse.
Well, I mean, yes and no. Again, if you want to characterize it that way, you're free to, but that doesn't capture the nuances that are present when you're doing complex cosmology. That's the thing. Like I said, it seems more an attempt to make the idea sound absurd. Oh, they could fit the planet Earth inside my purse. Like nobody's saying that like we took a planet. Nobody's saying that like we took a planet and we put it inside of a purse. But you can take matter and make it very, 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 very small and retain all of that energy. That's a thing that can happen. The Earth could become a black hole. It wouldn't be any larger than a marble. That's 100% physically possible. So when you talk about this as if it's absurd, well, then you just don't understand physics. Physics, there's nothing wrong with this. This is a thing we do all the time. Well, these states of matter exist all over the universe.
The Earth being the size of a marble pales in comparison to what we're saying here. We're saying that galaxies upon galaxies were smaller than in a space marble.
Well, that's because they weren't galaxies. You're thinking that but somebody took galaxies as an object.
Was necessary to make them.
You keep thinking that like galaxies as an object were put inside of like a container that's really small. That's where you're losing this. That's not what happened. The universe isn't a container. That's not how it works. So, and this is where you kind of do have to get into the math. Do you know what happens if you compress a space? Like if I took a coordinate space and I compressed it, what would happen to 2 points in that space?
They'd get closer together.
They'd get closer together. So what happens if you have two objects in space-time and you compress space-time?
Well, they're
going to get closer together. Right. So what happens if you just took space-time and compressed it to the point that material objects couldn't exist anymore because the universe is too high energy? Are you saying that can't happen?
I'm saying extraordinary claims require extraordinary
Sure, but that doesn't answer my question.
No, look, can it? Look, I believe in God, so could God do that? Sure. I have no problem with that. But we're not talking about God and what he can do. We're talking about what happens by physical processes, physics that we observe. We're talking about science. We're not talking about myth, right? Or are we? Because this is exactly what this is. Because right now, you want me to believe this extraordinary claim on the basis of two things. One,
actually four things.
Radiation. We see radiation, and then we see a redshift. Okay.
Well, I listed 4 pieces of evidence.
Okay, you listed.
What about the solutions to Einstein's field equations?
No, but I don't. General.
So let me ask you a question. Do you think space-time is expanding?
We can get to that in a little bit. I think there's good reasons to doubt it, but I'm granting it for right now. Okay, I do have reasons to believe that it's not, but we can get into that later. Right now, I'll even grant you expanding space. Even if I grant that space is expanding now, that doesn't tell me that it was once in a singularity, right? Now.
But what happens if you just like rewind the clock and you had something that was like if you had a balloon that was expanding and you recorded it and played the tape backward, what's going to happen? What are you going to see?
Well, first of all, you don't know what the starting point is.
No. That doesn't have to do with what I asked you. If somebody recorded themselves inflating a balloon and you took that recording and played it backward, what would you see?
Well, you would see it completely deflate.
Okay, so if the universe is expanding, and I'm dealing with conditionals here, if the universe is expanding, then that would just entail that earlier in its history, it would have been more dense than it is now. For the same reason that if you're inflating, you don't need to. If you're inflating a balloon, let's say that the recording, you don't see the person inflating the balloon. All you see is part of a balloon and it's inflating. You rewind the tape. What are you going to see?
Well, I'm not going to see it as existing as a singularity, which is
sure, that's fine. But I didn't ask you what you're not going to see. I asked you what you are going to see.
But you're telling me
I'm not telling you anything. I'm asking you a question. What are you going to see?
Leo, I know the starting point of a balloon. Right?
I'm not asking about the starting
point of the universe.
I'm not asking a starting point.
And I already answered your
question.
It's
a simple question. Well, I changed the question. I changed the question.
I would see a deflated balloon.
Even
That
when you
doesn't
don't
help
see
me
the balloon
understand
getting
what happened
inflated,
with the universe.
even when you don't see the balloon getting inflated, if you saw it inflating, but you don't see the person doing it, if you rewound that tape, you acknowledge you would see the balloon deflating, right?
Yes, but why do I
Okay,
know
so
that?
then that
Because of my
entails.
prior observation.
So then that
Does not
entails.
entail anything about the
Well,
universe.
well, so you're saying that seeing a balloon inflating doesn't entail that prior in its history to that point it was smaller? You don't think that that's? I would think that that's just an illogical entailment of what the concept of expansion is. If something is smaller now and I expand it, then obviously in its past it was smaller. Yeah, that's an entailment.
Okay.
That's what it means for something to expand. It gets bigger throughout time, which means if you go back in time, it gets smaller. So I don't know how you could, just granting that the universe is expanding, I don't know how you couldn't say that that doesn't entail, or I don't know how you couldn't agree that that entails it would have been smaller in its history, would have been less expansive.
Not smaller. I just
well, but that's what I was asking you. You said you don't see how it expanding entails that it was smaller in its past.
Right now, if it's expanding right now, then okay, yesterday it was smaller, but that doesn't tell me it started as a singularity.
Right. I haven't gotten to that point yet. I haven't gotten to that. We haven't gotten that far.
You said, let's go back to your 4 pieces of evidence, because I only heard 2, because I heard general relativity, but general relativity can be true.
Galactic redshift.
The Big Bang be completely false.
Well, actually, probably not. No.
Okay, explain this to me. Why would
because the solutions you cannot have a static space-time with a universe that looks like ours.
Okay, but does that mean that the Big Bang model is true?
Most likely, yes. When we tie that. See, the thing that you're getting is that you're trying to examine one of these at a time, independently of anything else, and trying to figure out how it shows the hot Big Bang model is true. But that's not how science works. Science doesn't take one thing, examine it, isolate it from everything else, and try to figure out what it shows. You're just going to deal with underdetermination at that point. That's why I outlined 4 pieces of evidence and built. We've got general relativity. Well, when we solve those equations for a universe exactly like ours, it can't be static. It's either expanding or it's contracting. It's got to be one of the two. So we know that. It has to be one of those two. So we're already start there. You can disagree with that, but at that point, I'm sorry, then you need to brush up on general relativity, because that is an explicit fact of reality. Space-time is either expanding or it's contracting. It can't be anything else, not with a universe like ours. So we start there. Then we observe galactic redshift. Okay, well, then that confirms it's expanding. Okay, great. Well, that entails that if we go back far enough, the universe would have contracted to a point where there would have been so much, like you said, sounds ridiculous, but you have all this energy packed into a space so small that even light just bounces around. It doesn't go anywhere, meaning that as it expanded from that state and evolved from it, we should expect to see that emission of light, because it should near uniformly fill space-time. We've observed that, the cosmic microwave background, and at the same time, the same event should have allowed for the formation of atoms, and they should have formed in about 95 to 98% majority, the 2 lightest elements on the periodic table, and that's exactly what we observe. So it's the corroboration of all of these pieces that I think paint a pretty explicit picture that the universe, very early in its history, was in a very hot and very dense state, and it evolved from that state.
Okay, so I've heard your evidence. For me, that is very weak evidence. Because number 1, radiation. Wow, that's surprising. I can think of other sources that could be causing radiation.
Yes, but not that kind of radiation. Not uniform to 1 part in 100, 1,000 in every direction that we look, regardless of the distance or the scale. So you don't have a way to produce a radiation like that. I do, and I've outlined what it is. So if you can give me something that reproduces this picture in a more parsimonious way than what I've presented, then I would like to see that. But I really don't think that you'd be able to do that.
Okay, I want to explore this more, giving you cosmic background radiation, giving you redshift. But there's something I have to do here for a moment, in case the viewers are starting to think that this is parsimonious with our observations. Now, and I hope you will allow me to say these things, Leo, without interrupting me, because this is an important idea that people need to understand. Based on those observations, okay, we can say that cosmic background radiation supports the Big Bang model. We can say that redshift supports the Big Bang model. However, many people are not aware that as the Big Bang model has progressed, it has gotten farther and farther away from actually corresponding to our observations. And it has now created so many hypothetical entities and free parameters that every time the model fails in its predictions, they create a hypothetical entity. Examples: inflation, dark matter, dark energy. Inflation, a free parameter that allows for
What do you mean by free
the
parameter?
fixing of free parameter, something that will allow you to fix things to fit the observational data. Now, so dark matter and dark energy, absolutely zero observational evidence for either one of these things. Dark matter is supposed to compose more matter than the regular baryonic matter, and yet we have no observational evidence of its existence, period. So if you are believing in the Big Bang absolutely needs dark matter, it needs dark energy. These are completely invisible, undetectable. And so, and we've gotten farther and farther away from reality as we've tried to hold this model together. So, and this has been pointed out. This is not just me pointing this out. This was pointed out by astrophysicists, a few brave ones who were willing to put their career on the line and speak out against this model and talk about the problems with it. And they usually just get, you know, ad hominem attacks. And so, Leo, I challenge you not to do that, but to actually address the problems with the Big Bang and how it has gone away from our observational data and just moved in the direction of totally making up stuff to make the theory work. And that includes and we may get into this later, talking about the discoveries made by the Hubble and JWST telescopes that had completely went and caused major problems for the Big Bang model, and what's being done about that now.
I do want to talk about, we can talk about dark matter, dark energy, but before we get there, you did mention inflation. I think that would be the best place to go to next, if that's all right with you.
Sure. And I just want to put this comment up right here. Travis says only we're allowed to make stuff up. Look, and I guess this is a comment.
Yeah, that's a privilege for us, Rebecca. You don't get to do that.
Well, actually,
only we get to make stuff up.
But this is the difference between science and stories, right? I believe a story. I believe the Bible. I believe in the beginning, God created the heavens and earth. That is a story I believe. You choose to believe that.
Can I ask what you mean by story?
There was a singularity and everything.
Well, I don't believe that.
Okay, well,
I don't think most cosmologists believe that.
Okay, you believe the Big Bang model. Is that correct?
Do I accept the Big Bang model? Yes, I accept it on the preponderance of evidence in favor of its truth. Yes.
Okay, well, we'll see. I haven't heard the evidence for it.
I've given it 4 pieces.
Okay, not enough.
I think you've questioned them, but you haven't shown why they're not evidence for the Big Bang, given that what we would expect to see. And see, that's probably another thing that we should touch on. We can either do it now or at some other point, is what we understand evidence to be. Because if we're working from 2 completely different notions of evidence, then it's going to be nothing but talking past each other. So I think that evidence is that which is expected given some model or hypothesis or something like that. It's what we would expect to see if that model were correct. And I think that if the Big Bang were correct, if it were true that the universe started out not really started out, because we don't know if that's true, but very early in its history, we're in a very hot and very dense state. I think that I've shown what we should what we can expect to see is a cosmic microwave background, and we see that. We should expect to see an abundance of light elements, and we do. We should expect to see that space-time is expanding, and we do. And we should expect that our mathematics that describe space-time would give descriptions of that, and that's what happens. And I've outlined those 4 pieces. So at least there's at least thus far 4 things that we should expect to see if the Big Bang model is true, and we see all 4. I don't know how that's not evidence.
Well,
You might not think it's enough
actually,
to not, sorry to cut you off, but you might not think it's enough to establish that the model is true. But I don't know how you could say that it's not evidence, unless you disagree that we've seen those.
Wait, hold up. I didn't say it's not evidence, though. I said cosmic background radiation can support your model, right? Mm-hmm. Redshift supports your model, mm-hmm. but it's not necessarily the only explanation for those phenomena.
Do you have another one? What's another one? Well, how else can we explain the CMB?
Well, you know, I don't know actually. But
well, then why would you doubt the model that we do have?
Well, because I do think it's a little, well, because I think there's lots of radiation causing, you know, there's possibilities in the universe that are not as absurd as that.
They can make a radiation like this.
Causing bodies in the universe. So
yeah, but uniform radiation to 1 part in 100,000. Like that's not the thing. It's not just that this is because I need to make this point, because I think that you're thinking that this is just like some radiation. It's just some light that's kind of out there. No, it's everywhere. No matter where you look, no matter how close or how far away, no matter what scale you're looking at, it is the same to 1 part in 100,000. Now, you're right. There are plenty of other ways, a myriad of ways to produce radiation in the universe. You're not wrong there, but they can't produce a radiation like that is near uniform, that is uniform and homogeneous, effectively scale invariant to 1 part in 100,000. If you can give me something that can produce a radiation like that, I and the whole of cosmologists globally are all ears open.
Well, but what you're not saying here, Leo, is the little problem with the CMB, which is called the axis of evil in cosmology. And
that's not a problem.
There are fluctuations. For those who may not understand what this is, there are fluctuations in that cosmic background radiation. And the weird thing that about this is that it corresponds to the elliptical plane. And so this is not to be expected if this is just radiation that's coming from the very edge of the universe. And it just, the fluctuations somehow correspond to the elliptical plane. So Leo, if you want to explain that, please feel free.
Yeah, so the axis of evil is this idea that when we look out at the universe, there seems to be a difference in temperature in the CMB, and that difference is aligned almost perfectly with the elliptic plane of our solar system. And the thing is that this is measured in the quadrupole and the octupole measurements of the CMB. There are at least 1,400 different poles that we can use to measure it. And by poles, that's just sort of like some mathematics that can be used to split it up and all that stuff. So it's only in 2 of the 1,400 that we see this. This is something that was that's taken by people like Robert Sunjanis, who I've debated. You can find that debate on my channel. It's really funny. He had a really hard time with understanding relativity. They bring this up and say, well, you can't explain this. This isn't predicted. Well, it's seen in 2 of the 1,400 different ways we can measure this. So it's just not statistically relevant.
Okay, well, you know, it is statistically relevant. So I argue with
how,
that, but I also want to.
Well, but how though? Okay? If you're going to say it's statistically relevant, you got to tell me how.
Well, I mean, look, I'm not an expert on this, but why is it called the axis of evil in cosmology? Why does it need to be evil? It's evil because it's happening in a way that it should not be happening if there's this cosmic background radiation. And I want to make another point about the cosmic background radiation, which is this: you called it smooth, right? And at one time they were saying, see, it's so smooth, and that predicts, I mean, that's what we predict with the cosmic background. And then guess what? We started to see the fluctuations. They started to be lumpier, and now they say, oh, well, actually, we needed it to be lumpy because we needed cold dark matter in order to create the galaxies and everything to form. So when it was smooth, that was predictive of the theory. When it was lumpy, then the theory changed in order to fit the lumpiness, right? So, I mean, this is observations I mean, when the model does not fit observations, then we just add in whatever we need to massage the model to make it work with the observations. That is not the scientific method, right?
What is not the scientific? Wait, so when you have a model,
when you change your parameters, when you make up hypothetical entities, when you change what you're looking for in
well, I don't
order
think that's
to
what's
fit.
going on.
Okay,
I think what we're doing is trying to account for observations.
Explain dark matter to me.
Well, I wanted to get to this lumpy versus smooth. You do realize that's on two entirely different scales of reality, right? Nobody predicted that the universe was going to be smooth on like galactic or intragalactic scale. That's not. It's the extragalactic scale. The large scale structure of reality of the universe is smooth. I mean, it's lumpy at the level of planets and stars and galaxies, obviously, but that was predicted. Its smoothness is on the large scales. Dark matter is I mean, you say there's no way to observe it. Well, there is actually. We've observed it gravitationally. We know it's there because galaxies, when they rotate, they're rotating effectively so quickly, and there's not nearly the differential we would expect from the inside parts to the outer parts. You would expect that as you get further out, it starts to rotate more slowly. That's not the case. It stays the same speed, roughly, from the center all the way out. These galaxies should be flinging themselves apart, but they're not. Their masses are also have as a result of gravitational lensing, we can observe. So we've got that effect that they're rotating at speeds where they should be flinging themselves and up, but they're not. It's flinging themselves apart, but they're not. And we can also observe that they're lensing light, bending light with their gravity more than what they should with just the baryonic matter, the normal matter that we can see. So,
okay, so
obviously there's more mass here. How would you account for this?
Well, maybe they aren't billions of years old, so they haven't flung apart.
That
yet.
wouldn't affect
That's
this. We can grant that they're 14 minutes old. That doesn't affect this. They'd still do this same stuff.
Well, I don't know, Leo, but I don't think you can make up matter, which and well,
actually, we didn't make up matter.
You want to look at Yes, you did.
This How so?
Well, you not specifically, but well, if you can't measure it, right? You
exactly. I just gave two measurements of it, though. Galaxies aren't flinging themselves up. Yes, I did. We observed that galaxies are rotating so quickly. I mean, you understand how like centripetal and centrifugal force work, right? If you take an object, like you can take, what do you think happens to like an engine in your car if it rotates too quickly? You might throw a rod or something like that. You might have, and I heard your husband talk about that. Maybe you know about engines yourself. I don't know. I'm not saying just because you're a woman, you can't know about engines because anyway, you can spin something fast enough that it like flies apart, that part because of the energy of its rotation. That's what's happening with galaxies, except they're not flying apart. They should be. Okay, so there's a discrepancy here. Now, so that's the first one. The second one, the light that is coming from other galaxies as it passes this one is bent, is lensed more than it should be given the mass that we know the galaxy has. Well, so we know that they have more gravitation. There's more gravity there than what there should be. It's lensing light more than what we should expect, and it's holding the galaxies together despite their rapid rotation. So, what do we know? I want you, Rebecca, to tell me something that you know can cause gravity.
Well, massive objects.
Okay, mass can cause gravity, right? Okay, so wouldn't it be reasonable to think that maybe there's a type of mass here, but it does not interact with the electromagnetic radiation? And so our telescopes that utilize like radio waves and X-rays and infrared and all that stuff aren't going to be able to see it because it doesn't interact with the electromagnetic radiation. But we would, because it has mass, be able to detect its extra gravity. It seems like a good fit to me.
You know what? That's a fine hypothesis.
That's dark matter.
How would you?
That's dark matter.
But how would you find out? How would you how would you observe this matter?
We're still looking for ways, and most cosmologists will tell you we don't even know for sure if it is like a particle, a type of matter. Because of the observations, the lensing, and there's a variety of other things with respect to like the CMB and galactic structure and all that. There's a lot of observations where these effects that we're seeing that we otherwise like. Okay, what's causing this? Are kind of what we would expect if there were some type of matter out there that just didn't interact with light and had mass. This is exactly what we would see if there was something like that. Now, we don't know if that's what it is. It could just be that general relativity works differently at larger scales. That's modified Newtonian dynamics, or MOND, which is different from dark particle, dark matter with respect to the two paths that cosmologists take to answering. So not even all cosmologists are on board with the notion of dark matter, but most are, because what we see, and again, this is what I think a prediction is you have a model. It says, hey, if this model's true, you should see this stuff out in the world. And so we see this stuff, and we should see this stuff if there is a type of matter that doesn't interact with light. That's why most cosmologists think that. It's what follows from what we see. It helps explain what we see. And so let's try to see if we can detect it. Let's actually see if it's there. And that's what cosmologists are currently doing.
Yes, and they have built incredibly large, expensive machines trying to detect what this matter could possibly be. And do you know the results of their experiments? Have they seen anything?
Have we detected it? Other than gravitationally? No. But we haven't had much of the similar. We haven't had any greater confirmation for modified Newtonian or Einsteinian dynamics either. However, most of our observations do best comport with a particle dark matter model.
Okay. Yep. Now, that is one hypothesis, and I'm glad you admitted that there's a possibility that the model could be wrong, right?
Of course.
Like, there could be a different explanation for why the galaxies and the issues with gravity and the issues with even the galaxy formation, those issues, there could be a different explanation for that rather than dark matter, right?
Yeah, there could be.
Okay. So good. That's where we're at. So we actually don't know.
Well, it depends. I mean, you say don't know, that's going to get into certain episteme. I mean, we know that there is a gravitational anomaly occurring here. We're just not certain. We've got good ideas for at least two really good ideas for what could potentially explain it. One's a little bit better than the other, and that would be particle dark matter and then MOND. But we don't know that those are correct. Particle dark matter is probably correct, and most cosmologists are going to say it's probably correct, but we don't know. And that's because of the observations that we make. They're exactly what we would expect if there's a matter out there that just doesn't interact with light.
Yeah, except that it's not like what you guys have done is, in order to keep those galaxies together, you've made math that fits, that makes the dark. Yes.
I can explain why not. Because we observe that these galaxies do not fling apart, but they should. They should if we're measuring the amount of normal or baryonic matter that's there.
But
they curve light more.
Okay, I don't know about the curved light, so you'll have to give me a source on that. Okay, I don't know anything about the curved light, but what I do know is that if you could just get rid of the Big Bang model, and then you wouldn't have a problem with the galaxies as they are, right?
Yeah, well, no, we still would.
How would you solve a problem?
Because like even if the Big Bang was like wrong, galaxies still have to like form somehow. I mean, that's another reason why we know that the Big Bang it's not wrong, is because well, I don't know how else you reproduce a universe that looks like ours. That's just going to be the big thing. Is good luck on that one. But yeah, I mean, if I could grant that the Big Bang model is wrong, but that dark matter, that whole issue would still be an issue. We would still need something to account for these gravitational anomalies in the in galaxies.
Well, there is another account of how the universe may have formed. It's not a scientific account, But I have no problem with galaxy formation. I don't need to hold desperately onto this absurd idea about all the galaxies beginning as a singularity. I don't have to hold on to that idea because I don't need that. I don't need the Big Bang Theory to work. But it seems that some people are so desperate for this model to work that they are willing to make up things like dark matter and dark energy, inflation, seeds, whatever else.
Well, but those weren't made up. You keep thinking those were made up.
Inflation wasn't made up. Okay, you wanted to go to inflation. Let's go to inflation.
Yeah. So if you want to share my slides again, because you even talked about some of the problems that the Big Bang model has. It has problems. There was the flatness problems where the universe is like geometrically or near perfectly spatially flat. The Big Bang model doesn't tell us why that is. Extraordinarily distant regions in space appear to be isotropic and homogeneous with respect to one another. The Big Bang doesn't tell us why that is. And the magnetic monopole problems. We don't observe magnetic monopoles. Why not? Well, the Big Bang doesn't tell us that. And that's where we get to inflationary cosmology, which is what is formed the basis of modern cosmology in the late 20th, early 21st century. So we've got the solution to the flatness problem, but I want to go to the magnetic monopole problem because this was the problem that was really kickstarted Alan Guth eventually developing the inflationary model. And so magnetic monopoles are objects that have one magnetic pole rather than two. If you took a magnet and you split it, you're not going to end up with one side that's completely a north pole and one side that's completely a south pole. You're going to end up with two magnets, both possessing a north and a south pole. We can observe things that possess one electric charge, and we can observe things that possess two magnetic poles, but we've never observed anything that possesses one magnetic pole, a monopole. So a lot of particle physicists were trying to figure out why, like, these are predicted by our theories. They should have been formed if, and see, this is the thing, is that if the universe really did, not really start out, but if it really were in a very hot, very dense state early in its history, it should have produced magnetic monopoles, but we don't see any. Well, why not? Well, there are a few different ways that you can sort of try to get magnetic monopoles to, well, effectively decay, so that you just wouldn't observe them because they've decayed into their decay results. And there's a particular type of phase transition, as it's called, that can in fact give rise to such a monopole decay. And Alan Guth was capable of working out all of the math and the physics with respect to this. And what he showed is that if very, very early in the universe, even before the hot Big Bang phase, if there was like a super cooling phase, a phase where the energy level of the universe just absolutely plummeted, I mean, afterwards, it still would have been several 100 million, if not billion degrees. So, I mean, it's you got to think at the scale here from where it's dropping to where it's not like it's getting cold. It's just not nearly as energetic as it was. This would have caused magnetic monopoles to decay. The supercooling would have dropped the energy level such that these magnetic monopoles decay. And when he did the math, and he incorporated it with some other things, particularly in with respect to cosmology and space-time, what he found is that what would have to cause this is some sort of like energy field. You would need a field, like a quantum field there, and the energy of it to begin to decay. And what this would do during this phase is it wouldn't just supercool the universe, which would lead to the decay of magnetic monopoles. It would also give rise to an extraordinarily repulsive force in space-time that uniformly fills it and lasts as long as this field decays for, this inflaton field, as it was later dubbed. And this is an exponential, this repulsive force would have given rise to an exponential expansion of space-time, or I mean, just expanding in almost some sort of label, the exponential. So, like, if you think about it, Rebecca, if we were both going to count to 1,000, and you're going to count the traditional way, 1, 2, 3, 4, 5, 6, 7, 8, 9, and I'm going to count 2, 4, 8, 16, 32, 64, 120, 128, something like that. Who do you think is going to get to 1,000 faster?
You will.
Yeah, because I'm counting exponentially. I'm taking whatever my last number was and squaring it, then taking that and squaring it. So I'm going to get there faster. That's what the expansion of space-time did. And this would have taken all the decay products of these magnetic monopoles and stretched them such that they would have decayed under the continued cooling as a result of the hot Big Bang phase, which followed this. And that would have meant that we don't see any magnetic monopoles, and we don't even see their decay results because of inflation. So when you say they made up inflation, no, they didn't. They were actually trying to solve a problem, because that's what scientists do. And in the course of doing so, discovered that this exponential expansion would merely be a result of this supercooling phase, that they would have gone hand in hand. So they didn't make anything up. It's what fell out of the math, because this is how it works in science.
But Leo, don't you see how beautifully you illustrated my point? Because you explained the problems that existed with the model, right? And then, okay, instead of saying, okay, maybe the entire model is wrong, maybe everything didn't fit.
But what would we expect to see then?
Maybe the universe didn't start off in a hot, dense state. Maybe that didn't happen. Instead of saying maybe that didn't happen, no, instead they say, well, what we need is for this inflation to happen, right? And so they added inflation.
But that isn't what they said.
To help figure out how the model save the model.
No.
Okay. They added inflation to save the model.
No.
Tell me how that's wrong.
Because they didn't add inflation. Inflation fell out of the solutions to the phase transition that was needed to cool the universe so that magnetic monopoles would decay.
What observational evidence do we have for inflation?
I was going to get to that, but I wanted to get to how it solves the issues that remain with the Big Bang. So everything that I've just explained is how it solves the magnetic monopole problem. That's what inflation does. It solves the horizon problem, because these like causally disconnected regions that look the same, even though they're causally disconnected, so they wouldn't have had time to sort of like mix to look the same, was because that prior to inflation they were really close together, and the whole universe sort of like could mix and become homogeneous prior to its inflation, where it would have remained homogeneous afterwards. And regions that were previously not causally disconnected are now causally disconnected, but they still look the same because they were once causally connected. So that's how inflation solves the horizon problem. And it solves the flatness problem because it would have stretched space out and made it near perfectly geometrically flat. And we've actually measured the curvature of space-time, and it's flat to 0.25%. So these three observations confirm that, help to confirm that there was most likely an inflationary epoch, but they're not direct evidence for inflationary theory. So then there is, in fact, direct evidence for inflationary theory. And the first one is going to be the upper limit to Big Bang temperatures, how hot it could have gotten once the hot Big Bang phase kicked off, immediately preceding the inflationary epoch. Because this is the thing, and this is something that I think Rebecca doesn't understand, no offense intended, is that the hot Big Bang is not a theory of the origin of the universe. It doesn't tell us where the universe came from. It doesn't tell us anything about the beginning. That's not what it does, because inflation comes before the Big Bang. And so after inflation, the universe, when it reheated after this supercooling, inflating phase transition, it could have only gotten so hot. And the upper temperature is about 10 to the 19th giga-electron volts, which is just, that's a way that physicists measure energy. And we know that during the Big Bang phase that these temperatures didn't exceed 10 to the 16th giga-electron volts, below the maximum limit, which provides strong observational confirmation that there was most likely an inflationary epoch very early in the universe's evolution. We also have the density perturbations in the universe, the sort of the clumpiness in the universe, which was seeded by the fluctuations, the quantum fluctuations in space-time, in all of the quantum vacuums that exist in space-time as inflation stretched them. those fluctuations would have been stretched, and this would have mapped to density perturbations, which we can see in the large-scale structure of the universe. Now, there's two interesting things about these perturbations, is that they should be adiabatic to nearly 100%. Adiabatic means the entropy between these perturbations should be almost constant to near 100%, and they should have almost zero isocurvature, or constant spatial curvature, between all of these perturbations. And when we measure the large scale structure of space-time, which we certainly have the ability to do, we measure that it's adiabatic to about 98.7%, very, very close to 100%, and that its isocurvature is about 1.3%, which is not far above zero, both of which are very, very close to predicted levels. And this again provides powerful confirming evidence that there was most likely an inflationary epoch that occurred prior to the hot Big Bang phase. We also have the fluctuations that exist.
Can I pause you right there, though? Right, I just want to pause you right there and kind of bring awareness, okay, that this is all assuming that your model is true.
No.
Okay. You've done a lot of storytelling.
That is not true. These are all observations. No, I'm sorry. I'm going to have to correct you there. These are all observations that we've made.
But you're observing it with hope of the model being
No,
true.
We're observing it and trying to figure out what best explains it. Inflation does. If you have something better, I and all other cosmologists globally are ears open.
Big Bang theory.
Yeah, but throwing out the model isn't giving something better than it to replace it. I don't think you have that.
You have to say, I don't know.
And they do say that we don't know.
Say, I don't know. But you can rule out things when they get too ridiculous. And I hope like people are recognizing that the observations that this model is resting on are extremely flimsy, and we can get into talking about how the redshift can be explained by other things. And
you haven't explained how.
I know we haven't gotten there yet. We're going to get there. Okay, we can go there next if you want. But I want to just address some of these comments. Germania says, I'm not trying to do a gotcha question or belittle you. Just curious. What do you understand about the Big Bang model? I'm sincerely curious. Well, just keep listening, Germania. I mean, maybe I'm not saying I have an expert level understanding on this. There's a lot of people that are way more educated than me and way smarter than me that probably know a lot more about this. I'm just trying to awaken skepticism.
Would you listen to them?
Is absolutely. I listen to people who are I think are giving me reasonable ideas, but this idea that's being promoted as scientific fact does not match up with most of our scientific observations.
Yes, it does. In fact, it's based on all of them.
We replace bad science with better science. It literally takes science to replace science. Science is a good guy. I totally agree. And that's why let's let the scientific observations speak. Let's let JWST show us some things about space, and we can talk about whether or not the discoveries of the JWST telescope match up with the Big Bang model. They absolutely do not.
Yes, they
contradict it in
way.
every
So why do all the experts still hold to the hot Big Bang model? Why do all the experts still hold to the hot Big Bang model? You just admitted these experts know way more than you. Okay, so why did they still hold to the model if it's completely wrong and none of the observations support it? Give me the reason.
Well, I mean, now you're asking me to speculate about what's in the mind.
Yeah, I am. You want to speculate about that, though. You claim these models are wrong, but then you admit that there's a bunch of people that know way more about the subject than you do. Okay, so why do you think they're wrong?
I'm going to tell you because of our observations, because the observations they themselves are making.
What observations?
Well, okay, let's talk about what the JWST saw, right? We have observed more distant galaxies than, first of all, than the Big Bang. The Big Bang did not predict that there would even be mature galaxies out at that distance, because the Big Bang model predicted that we wouldn't even have galaxies forming until like 1 billion years later or something. Okay, so there weren't supposed to be
that's not entirely true.
The Big Bang model also did not predict that we would even be able to see them out at that distance, because their brightness was supposed to drop off. We weren't supposed to be able to see them. Because if space is expanding and their distance is getting farther, we weren't even supposed to be able to see them. And in fact, if you listen to, people talk about what was expected with the Hubble telescope, they said, don't even bother building cameras to see the distant galaxies because you're not going to be able to see them. Okay.
So then why did they build those cameras?
Then we also have the observation. Well, I guess, I don't know.
They must have thought that they were going to see something. Why would they have wasted the money? It's almost like whoever said not to build that had like something, that they were trying to, prop up.
Okay, but what else did the Big Bang not predict? Well, I mean, the Big Bang predicted that we would see a lot of colliding galaxies. The Big Bang predicted that
we do see that.
There would be okay. So you're saying that we saw as many colliding galaxies as we needed.
The Big Bang didn't really make predictions about like galaxies and stuff. Most of that comes from other assumptions cosmologists have put in based on the simulations set up to the current point we've been capable of doing. They don't come directly out of the Big Bang. Now, see, this is the thing, is that the hot Big Bang is one small part of the whole model of cosmology. Now you're getting into galactic formation and stuff like that. That's different than Big Bang. And cosmologists worked from the assumptions that they could make based off of their simulations. We don't live for 200 and something odd million years. We can't just watch a galaxy form and, write down every step of the way. So we have to run simulations. We have to look out into the universe. We have to work within the technological limitations that we currently have. And then when we develop better technological devices, we will adjust our models as they give us data so that we can say, okay, well, we thought it might be this. It's actually this. We thought you might not be able to observe galaxies, back this far, but actually you can observe them back a little bit further. That doesn't confound the hot Big Bang model. Not at all. Not even remotely. This is how science works. We start from what we know, and then as we collect more data, we make the proper adjustments until we get a really good, solid model. But we're not going to abandon what we already know simply because it's not complete.
Okay, but do you assume that the model is correct?
No.
From the beginning, and don't allow your observations to guide? I mean, this observation.
See, that's the thing. You're assuming that the lambda CDM model wasn't developed on observations, except that it was. And I've gone through a handful of observations that cannot, at least as far as we know, that cannot be nearly as parsimoniously explained by any other model than the lambda CDM model. And all you've seen to do is just say, well, I don't think that's evidence, and I don't think that those observations confirm your model. There's other ways to explain it. And then when I ask you what those ways are, you say, well, I don't know them.
Okay, well, let's talk about then possible other explanations for the redshift, right? Because that's actually probably the best, right? Observational support for the Big Bang model, right?
Well, I think the best observational support is the cosmic microwave background. I think that effectively proves the Big Bang model.
All right, well, you know what? I mean, that may be enough evidence for you, but to me, this
and
is
for
an
pretty much like all cosmologists on the planet, and most people who are not necessarily cosmologists themselves, but like understand the field, like me and Andrew Cumming, who's in the side chat. Hi, Andrew.
What do you have to say to Michael Disney, well-respected astrophysicist, who says that this model is more like a folktale constantly re-edited to fit inconvenient observations? He also says this. Okay, let me find it. He says, in a robust astrophysical field such as stellar structure, there would be many more confirmatory observations than free parameters. In contemporary cosmology, this turns out not to be the case. Indeed, as we shall see, the number of free parameters probably exceeds the number of relevant independent measurements, as it has done throughout history, with no sign of convergence between the two. Just because professionals cling to such a flimsy theory,
I'm still here, by the way.
Okay.
I just shut my camera off real quick.
No other within their grasp need not discourage the rest of us from being a good deal more detached. Okay, that comes from Michael Disney, retired from Cardiff, professor, Cardiff University.
Cardiff, yep. I know who he is.
Okay, all right.
Seems like a pretty decent guy.
Okay, so he what do you say to his what he's saying, that this is more like a folk tale that is just re-edited to avoid inconvenient observations?
Well, that's just this guy's opinion, right? Like all you really did here was kind of just like quote mine somebody, but you didn't really like give an argument. You just said, well, this guy thinks that this is a bad model. What do you think about what well, hold on here. I don't really care what Mike Disney thinks. I care what the consensus of relevant cosmologists over several decades and all of the concordance evidence that we have has to say. I don't care about, cherry-picked professionals that you're only citing because they agree with the preconceived notions that you hold to. I care about where the evidence points, and my camera will be coming back on in a second. I care about where the evidence points and what the consensus of the experts has to say. So I just don't really care what Disney has to say about this.
And I don't care what the other astrophysicists have to say, because I'm not willing to farm out my critical thinking to experts. Okay. I can still think critically. I may not be an expert in the field, but I can understand enough to understand that this is absolutely absurd to think that all the stars, planets, galaxies once existed in a speck, the space the size of a speck, and then exploded and formed an orderly universe.
No, the Big Bang wasn't an explosion.
If you don't believe in Santa, if you don't think Santa has enough room in his sleigh for toys to bring across the world, then why would you believe this absurd story about this universe coming about in this ridiculous way? I don't care how many experts believe that. I brought up Michael Disney's quote because you were appealing to experts. So I brought you an expert.
Sorry, which experts have I appealed to?
You said all of these all of the people in this field, all of the experts in the field, why don't you just listen to them? And I'm
I don't think that's what I said. I think I said that I prefer. I think that I said that I prefer to trust not just the expert consensus on the matter, but also all of the evidence upon which the expert consensus is based.
And, I'm looking at the evidence too. We're just seeing two different things here.
Can I ask you a quick question?
Sure.
What does the letter Z represent in cosmology?
The redshift.
Okay, that was very, very good. Do you know what baryon acoustic oscillations are?
No.
Do you know what a power spectrum is?
No, but why are you doing this?
Well, so I'm asking these questions. I'm asking these questions because you say you're looking at the evidence, right? And so there's nothing wrong with that. There's nothing wrong with looking at the evidence and examining for yourself. I encourage people to do that. But at the same time, if you're examining evidence and you don't understand very, very basic aspects of the field that anybody who in their first year undergraduate course would be taught, you're not really in a position to examine that evidence and come to the conclusions that it's right or wrong without appealing to people who know infinitely more than you do. So you can't just say, well, I've looked at the evidence and I disagree with it. But that's fine. But do you understand what you're looking at? Do you know the history of this? Do you know how these were developed? Do you know the arguments for and against this? That's what's going to matter here. Not just I looked at the evidence. You've got to understand it too. No, it's like what Nathan said to Sal, who has generously graced us with his presence in the chat. You have all these books, but have you read them or have you just bought them? There's a difference between looking at evidence and understanding that evidence and being able to know what's being said by it and how to fit that in with the broader framework. And I have to be honest, because there isn't really a soft way to put this, but I'm skeptical of your ability to do that with respect to specifically cosmology.
Oh, yeah. I'm skeptical of my ability to do that too. Okay.
So then that's my question. Then that's my question is that if you don't understand this, why are you so unwilling to think that, well, look, do you just not care that there are people who study this? Do you not think that it's worthwhile to ask them about these things?
Oh, I do. I'm happy. Look, if any
so why do you think they're wrong?
If any astrophysicist wants to come on and correct me, I'd be happy to do another show. Please, I welcome it.
Yeah, but what? Then
So
why do you think they're wrong? If you acknowledge that they know more than
I
you, and you
wanted, I
acknowledge that you don't understand the equations and you don't fully understand these charts, but then the people who do, you're saying, "How?" But they're wrong about that stuff. How do you know that?
well, look, I'm looking at the evidence that's being presented. You
But do you
presented some
understand it?
evidence.
Do you understand the evidence?
Yes, I understand it to the degree that I need to still believe that it's not enough at all.
So you're saying that I understand the evidence only to the extent that it allows me to maintain the beliefs I already have.
Well, is that what you're doing, Leo?
No.
Okay.
I think that I've outlined, like I said, at least half a dozen different independent lines of evidence that all corroborate the same picture.
Now you went from 4 to half a dozen, and I
Well,
haven't.
because I've went through
I've
more
only
of my
heard two.
slides,
I've only
and
heard two.
I've outlined
And
Einstein's
they're not
general
enough.
theory of relativity, galactic redshift, the cosmic microwave background, the abundance of light elements, in the inflationary epoch, and how that explains.
Hold on, slow down. Inflationary is a way of explaining away problems. It's not evidence.
Well, no, it's
Okay.
not really doing
So
that.
then what
Well,
was
actually,
the
yeah,
other-
it is. It is explaining away problem because that's what
Okay,
science
so
does.
it's explaining away no,
Mhm.
science is not explaining away problems.
Literally,
It's
that's what it does.
observing
Yes.
the world. It's
And then using those
observing-
observations to develop explanations that say, hey, there's this thing happening and I have no idea how it's happening. That's a problem. I have a problem of understanding what's occurring. So let me, observe what's going on, develop some hypotheses, observe a little more, refine my hypotheses, run some tests, figure out, okay, let me develop an idea here. What does this idea tell me? Okay, so, I'm thinking that maybe this should happen and that should happen. And if that's true, I should see this. Let me go see if I see that. Oh, I do. I see that. So there's a check mark. I should also see this. Do I see that? Yep, I see that. That's another check mark. This is how science works. So yes, it explains away the problems in our ability to understand things. It fills those gaps. It helps us understand more about the world around us. Yes, this is how science works.
Yeah, no, it helps us understand the world around us. But when there are problems with the model, right? And it repeatedly fails predictions and it can't work according to our observations and our understanding of physics. When it can't work, you don't just make stuff up to fix it. And
that's
that
right.
is what
we haven't
the Big
done
Bang
that.
Theory does.
No, the Big Bang is in line with the evidence.
Oh my goodness.
You keep saying that it's not in line with the evidence, but you haven't explained how we can have an expanding universe. You haven't explained the cosmic microwave background. You haven't explained the abundance of light elements in the early universe. You haven't explained the scale and variance of density perturbations in the universe. You haven't explained why the universe appears flat. You haven't explained a variety of these things. And science does. It might not do so perfectly. It might not have explanations for everything, but it's actually developing further and further. And the James Webb Space Telescope is evidence of that. We are now getting better, more accurate data about things, and we're refining our models to fit that, because that's how science works. That is not what you are doing.
Wait a minute. How did Big Bang model become equated with science? Okay, I am for science. What we're doing right now is we're talking.
Science is a process.
Science. We're not okay, but I'm for science. So don't make
for
this.
The process,
Rebecca
right.
doesn't believe in science. Rebecca doesn't accept science. I do accept science.
Well, what do you mean when you say that, though? Are you saying that you accept the processes we use to understand things? All right.
Yes, absolutely. I embrace that. I welcome it.
Does it also?
For it. I'm
does
absolutely grateful for our scientific discoveries and the scientific method and using that to improve our lives and to figure out the world. I'm absolutely for that.
Are you
what
also
I'm trying to expose is that you believe an origin story.
No, this isn't an origin story.
Not well supported.
Didn't I say that at the beginning, though?
Science.
Didn't I say at the beginning that the Big Bang isn't a model of the origin of or the beginning of the universe? That in fact we don't even know if the universe has an origin or a beginning. So how could this be an origin story when it doesn't even extend into the inflationary epoch, which precedes the hot Big Bang? It's just I kind of don't know what to say. Have you been listening to anything that I've been outlining?
Okay. Is it a story about the universe's history?
Well, what do you mean by story? I'm not sure I understand what you mean when you use that word. Like, do you mean like the telling of some events? Like, is that all that you mean? Telling about some events
that we actually we don't know if they're true, but you're
well, then the
telling
Big
of
Bang would
events
not be
that
that,
have.
no.
Okay, well,
Because these events are true. We know that they happen because we've observed them. We've watched it. We
okay,
can see
then
it.
so okay, then we've watched it. Okay, what have we watched? So we've watched.
We've measured the cosmic microwave background to ever increasing accuracy. There is no other known process that can produce a uniform, near perfect thermal blackbody radiation that permeates all of space-time and is largely scale invariant and is uniform and homogeneous to 1 part 100,000. We have observed galactic redshift. We know that space-time is expanding. We know that it's accelerating in its expansion because we've observed that. The concordance model explains that. There isn't any other model that does. We've observed that there is an abundance of light elements in the universe. The concordance model explains that. No other model does. And we've run tests on general relativity. There is no test that general relativity has ever been subjected to that it's failed. Not one, not ever.
Okay, first of all, I don't accept that general relativity is evidence for the Big Bang model. General relativity.
Well, then that just tells me you don't
true.
understand it.
Really?
Yes.
Okay. So
well, so do you what is it? Go ahead.
General, okay, you're saying because Einstein showed that we have to be moving, basically. We're either expanding or collapsing.
That's not, no.
Okay, then that's the way I heard you say it. So then explain it.
Well, that the equations, when you solve them for a universe that looks like ours, you can't get solutions that model that universe that looks like ours, which is what we want, since we want a universe that kind of, models the one that we see, where space-time is static. Static means essentially not expanding or contracting or like doing some form of motion. So yeah, general relativity tells us if this is what if the universe looks like the exact universe that we live in and see around us, space will either be expanding or it will be contracting, but it cannot be in a state of doing neither. You cannot have that. You cannot have that in a universe near uniformly filled with matter and radiation. That cannot be the place. If you think it can, show me the math.
Okay, but how does that support the Big Bang model?
Because it means that either the universe is expanding or contracting. So in either one of those, there's going to be interesting things to look at. If we have a hot Big Bang model, the universe should be expanding. I think that even you would agree that if the hot Big Bang model is true, then the universe should be observed to be expanding, right?
Sure.
All right. Yeah, when we observe that it's expanding. Okay. And we've measured that expansion pretty damn well through a variety of different ways, and they don't even agree with each other.
Okay, but is it possible, Leo, that the universe, and I don't accept necessarily that the universe is expanding, but let's just suppose for a minute that it is, okay? Mm-hmm. If it is, does that mean that the Big Bang model is true?
If space is expanding? I mean, effectively, yes.
Okay, well, I disagree with that.
Okay, but so why? I don't find why do you disagree with that?
Why? Because you're assuming that it has to go back to a particular point.
No, I'm not.
And
we don't know how far back the universe goes. I'm not assuming it has to go back to any particular point. The Big Bang is more general than that.
Then, okay, what if it, and oh my gosh, this is just getting insane. Let's go to expansion then. Let's talk about expansion and the problems with it. Okay. Are you, can you tell me what the rate of expansion of the universe is?
If we utilize measurements based on the cosmic microwave background, it's about 67 kilometers per second per megaparsec. If we use the standard candles measurement, it comes out to about 73 kilometers per second per megaparsec. Those should not and see, notice how I have no problem admitting where there's problems in our model, because I have that much confidence in the places where we know what we're looking at and we know what explains it. Those measurements should not disagree with each other to even close to that. And people say, well, 67, 73, that's only a factor of 6 or a difference of 6. Such that no, that is not okay. There's something going on. We don't know what it is, but those should not disagree. But it doesn't matter that they disagree, because both of the measurements, because not to what we're talking about, the expansion, because both of them still tell us that space is expanding.
Well, do they? Because
Yes.
there's evidence that it's not expanding. Now, so we can go to what the JWST, but I'm glad you brought this up because this is right. Our when we try to measure the rate of expansion of the universe, we get very disparate, right? You just said this.
Yep.
We
Yes.
get disparate measurements.
That is correct.
So we get measurements that do not agree. So that shows us that something is wrong, right?
Yes,
now,
something is wrong with how either, and I sorry to interrupt, but I want to provide this clarification. Something is wrong with either how we're measuring it, or something is there's something that we need to include in the models that we're not including. There is the idea that the universe isn't expanding is not even remotely deducible or inducible from the fact that we have two disagreeing measurements, because both of those measurements are still a measurement of the expansion rate of the universe. So it's just given that it's expanding.
Okay, so can you talk to me about the problem of dwarf galaxies?
I didn't know they were a problem.
Okay, well, they are a problem.
How so?
Okay, because well, we're looking at, and by the way, distance can correlate to redshift without there being an expansion in space. Okay, so there are scientists out there that are saying, yes, redshift goes according to distance, meaning like the farther we look out in space, the more distant the galaxy, the more it will be redshifted. That doesn't mean that it is expanding and getting farther away from us. Okay. And if we calculate the redshift according to just a flat distance without adding in the expansion, then when we look out at the distant galaxies, guess what? They correspond very nicely with their volume, with their size, with their brightness. They correspond very nicely to the galaxies that are nearby us. Okay.
Of course.
Now
that's what we would expect.
But when we add in expansion, then the galaxies that we observe in the distance are hundreds of times brighter, smaller, but in structure wise, they look the same, but they are impossibly small, impossibly dense. And this is a known problem in cosmology, Leo.
Galaxies probably just looked different when they were older, because the further out we look, the older the galaxies are. That's why most of the quasars that we see are billions of light years away.
Okay, so then what about, and this has been talked about a lot, but what about this thing that came out as they were getting the JWST, this paper that came out, Panic at the Disks. Okay.
Yeah, what about it?
Talking about okay. So what is the panic? Let me tell you what the panic is. Not observing what we think we should observe. The formation of galaxy structure was much earlier than previously thought. We have over 10 times as high what they thought of galaxy population. Okay. That the galaxies are not as highly clumpy and asymmetric as they thought.
Sure.
And that there's a problem with the distant galaxy morphology as observed by the JWST.
I kind of already answered this. Though.
Wait, listen to this though. I want you to hear this one too, about these galaxies. The median, these galaxies, this one in particular is talking about the four most distant galaxies that we observed with the JWST. These galaxies have median star formation rates comparable to the present Milky Way, despite them being more than 100 times less massive. So something absolutely weird is going on here. If we try to calculate and add in this ridiculous expansion, then we have a problem with all these galaxies. They don't make sense.
Well, we don't have a problem because the universe is expanding. We have a problem because we don't understand precisely how galaxies formed. So yeah, like I said earlier, everything that we thought, yes, you're 100, everything you said, great. on the money. The James Webb Space Telescope showed that a lot of things that we thought with respect to galaxy formation, what we should see, were not true. But that's not because the universe isn't expanding, has nothing to do with that. That's because the previous models we had with respect to galaxy formation weren't very well developed. We don't have a lot of information about that. How could we develop like precise? You're acting like that models not being precise or accurate somehow means they must be completely wrong. That is just not even remotely how science is done. We take the parts that we know are correct, we try to infer things from that, and if we find out that those inferences aren't quite accurate, then we amend them.
Yeah,
that's
and what's
happened
here,
all the time throughout the history of science.
But what I'm saying here is that if we just remove this idea of redshift equaling expansion, okay, and we just say redshift, whatever it's caused by, could be plasma, could be, whatever the other theories are, because there are other theories about explanations for redshift, movement through Wigner crystals, light scattering. There's other ideas about what could be causing the redshift. It's not necessarily expansion.
They're not very good ideas, though.
No, but if we just take the redshift as a correlation to distance, then the galaxies that we see in the farthest distances are very comparable to the Milky Way and other normal galaxies.
Of course they are.
We see. So okay, so then why not consider that maybe we aren't expanding? Why not?
Because there's no evidence suggesting that.
The measurements themselves are the suggestion, Leo.
No, they're not. They don't suggest that the universe isn't expanding.
Yes,
there's nothing in no, there's not. There's nothing
Leo,
in cosmology that suggests that. Nothing.
Leo, the Tolman surface brightness test, right? Is it, you could consider that a good test for whether or not this expansion model is good.
No.
Okay.
I actually don't think that's correct. I could be wrong. I've only heard like one thing about the Tolman surface brightness test, but I'm pretty sure I heard that that's actually not how we would test expansion. We would look for something like redshift, because if the universe were expanding, we would expect that there would be a redshift in the emission spectra of very bright cosmological objects that would be directly proportionate to their distance. Funnily enough, we observe exactly that. Now, you are more than willing, more than you have the ability to say, well, but I don't think that's a result of the universe expanding. Okay, then what is it?
What is your evidence? Okay, since redshift could be something else. Okay, what is your evidence that the Earth, that the space is expanding? That the universe is expanding?
Galactic redshift.
I just said redshift.
Well, general relativity too. So you put those two together. Space-time either must be expanding or contracting, and we observe that distant, very, very bright objects have a redshift in their emission spectra directly proportionate to their distance. Tie that with the idea that the universe must either be expanding or contracting. Well, that definitely comports with the universe expanding. It's good evidence that the universe is expanding.
Oh my goodness. Okay, and so it's no problem, and I'll just put up this picture, this chart that shows, and let me see if I can find it. Okay. And this came from Eric Lerner's website. I'm sure you know who he is.
Yeah, I do. He's not well respected in the field of cosmology.
I know he's not well respected because he doesn't. He's actually standing up against this model.
Yes, and he's getting a lot of things wrong and refusing to back down when it's shown that he's wrong, which is not something that's accepted in science, and it shouldn't be.
Show me someone who has responded to his data here. About the problem of these galaxies. Okay, the galaxy GHZ2 that was observed with the JWST telescope. If there's no Big Bang, no expansion, everything fits within the parameters of galaxies that we normally observe.
Yes, now, you know why that is, right?
And
can you tell me why that is?
Yeah, because he's just using redshift as as it corresponds to distance, rather than adding in the calculations that account for expansion.
Well, yeah, but you didn't explain why that is.
But well, I don't know what you're wanting me to explain, but look, if
we don't consider expansion, that distant galaxies would look a little bit more like ours. That's what I'm wanting to explain. Why?
Okay, hold on. Let me get to this because I still don't quite
I'm sorry.
understand what you're saying.
No,
But I want to get the information from the chart out.
Mm-hmm.
Look, if we calculate in all the Big Bang expansion, then this galaxy has a volume brightness that is 14,000 times the average galaxy that we observe in the nearby space.
Yep.
So that is insane.
Not really. I mean, it's an older galaxy. You have to remember, Rebecca, the galaxies that we observe 10, 8, 12 billion light years away don't probably even actually exist anymore. They're also 10 or 12 or 14 or 18 or 22 billion years old. Well, not years old, and 22 billion because the universe isn't. But the further back we look, the older we're looking. These are older galaxies. They have a different structure than galaxies today that are obviously not as old, because like people, galaxies and stars and planets change as they age. So the further back we look, we would expect to see that galaxies don't look like the galaxies that we see closer by, because they're much older. And like I said, you're right on a lot of this. We do not know really a lot about how galaxies formed. That is a thing that humans don't know a lot about. But that doesn't mean that our entire cosmological model is wrong. That is simply not how it works. You hearing you see, this is like a hypothetical, somewhat contrived, but it makes my point. So just bear with me here, please. You see me walking down the street, and you notice that there's this like metallic jingling sound coming from my pocket. Well, the fact that you don't know if it's coins or maybe like jewelry or, I don't know, nails or like some sort of like fastening equipment or something like that in my pocket, the fact that you might not know which one of those it is doesn't somehow mean that you didn't hear a metallic jingling. You still heard that sound. You just don't know what's making it. The fact that you don't know what's making the sound doesn't somehow mean you didn't hear it. No, you just don't know what it is. And so not having evidence for certain things doesn't make a whole model wrong.
No, but when you have to keep making up hypothetical entities to keep your model intact, then it might be a good clue that your model is wrong. And so let's just take the example from history, right, of the geocentric model. It made a lot of good predictions, but what did they have to keep doing? They had to keep adding in the epicycles and all these things to explain the motion of the planets, right? And they did that for a long time. They kept adding epicycles every time one of their observations didn't match reality. But guess what? The entire model is wrong. And that's exactly what's happening with the Big Bang model. Every time an observation doesn't match, a new hypothetical scenario or model or entity is made up to try to account for the failed prediction. And guess what? The failed predictions are mounting and mounting and mounting. And
can you name 3 of them?
Failed prediction, colliding galaxies, right?
We see galaxies colliding.
Okay. The failure to be able to calculate the expansion rate.
We've calculated it.
Even though, okay, but you admitted that we have 2 different ways of calculating it, and they give completely different answers. They don't even overlap.
The standard candles one is probably the one that's most likely incorrect. The CMB is at least. Now, Andrew might be able to correct me on this because he's the only other one here in the chat that I've seen that I trust with respect to more advanced cosmology. But as I understand it, most cosmologists would say that most cosmologists still prefer to use the CMB measurement, the 67 kilometers per second per megaparsec, rather than the standard candles one, the 73 kilometers per second per megaparsec, because they figure that the cosmic microwave background is kind of a little bit more reliable of a standard to use than standard candles are. Just so, and that's just from what I kind of have gathered. So I'm not going to say that that is correct. I could be very wrong on that. It might be the case that cosmologists are like, no, we actually really don't prefer that one. But what I have gathered from my reading and my actual direct engagement with legitimate professionals in this field is that I get that kind of. So we have measured it. We're not, it doesn't matter that there's, I mean, the only reason we're concerned about these measurements disagreeing is because we want a precise measurement of what the accelerated expansion rate is. But we know that the universe is still expanding, and we know that it's still accelerating in its expansion. And we know that very early in its history, it was in a very hot and very dense state. Not being able to get a precise measurement on that expansion rate does not mean that the universe isn't expanding at all, for the same reason that not knowing what's causing the jingling in my pocket doesn't mean that there isn't anything causing it in my pocket. There is, you just don't know what it is. The universe is expanding. We just don't have a super accurate measurement of the rate at which it's happening.
Okay. Well, it's interesting that you said that the standard candle model is probably wrong, or a way of...
well, that's kind of my opinion on it. Now, I think it's less accurate.
What was interesting is I was listening to this astrophysicist, Dr. Becky. Do you know who she is?
Becky Smethurst at the University of Oxford. Yes, I do.
Thank you. Okay. So, and she was saying last year before the JWST, she was like saying, I'm really excited about these JWST results because we've had this crisis in cosmology. And you know what? Either one of these two things has to be. Either our model is wrong, or we are over accounting for brightness on the standard candle test, right? Or a way of calculating. Now, she was hopeful that JWST would show that actually the Hubble telescope, when it took its observations of the Cepheid variable stars, right, that maybe there was, there was not enough, the transmission was too fuzzy. It wasn't able to accurately, and we over accounted for brightness. So JWST has better instrumentation. And so actually the results that have been coming out is that JWST and Hubble telescope, their measurements of the Cepheid variable stars are right on. And so then that wipes out the number 2, the standard candle problem that you were talking about. So what was her other alternative? She said, or our model is wrong. So
our model with respect to what?
With the Big Bang model. There's something wrong with it.
That's not what she meant.
Okay. What did she mean?
She meant the specific model being used to map that specific feature. Not that like the whole of cosmology is wrong, but a specific part of it might be. And that's true. There might be specific parts of cosmology, and probably are, that are wrong. Because we've just made the wrong inferences from the extraordinarily limited data that we currently have. Because again, we don't know. Like, it seems to me that you think that if a model isn't 100% correct on everything, everywhere, all the time, and in all ways, then the whole thing is completely 100% wrong. No, that's not. Well, it's what it sounds like, because you keep pointing to these things and saying, well, yeah, but these are things that the Big Bang has sort of been wrong. And half of these aren't even like specifically the Big Bang. They're other things that like maybe tangentially relate to that. So I mean,
no, what I'm saying is the observational evidence for this theory is weak compared to the amount of salvation parameters it needs to keep it afloat.
Yeah, but when you say salvation parameters, it seems like you're saying that these are things that are just sort of like thrown at the model with the hopes that they'll stick, but there isn't anything indicating them. And then that's just false. I mean, inflation wasn't thrown at the Big Bang and it stuck because people were like, well, this fixes all these problems because I just decided to say that. It's that, hey, this thing actually provides meaningful explanations that fit within the paradigms that we've developed and seems to reproduce the kind of universe. It produces certain features if it were the case, and those features are exactly what we see. So it seems that we've got something meaningful here with respect to this model. We should take it and work from this model and see if we can't refine it and develop it more and see if we can't get some more accurate ideas with respect to how our universe works. But this definitely seems like a good starting place. And that's what scientists do. And then they did exactly that. And they figured out, yeah, no, inflation is definitely a solid foundation for starting from with respect to understanding, theoretical cosmogony, because it helps us better understand why the universe looks the way that it does. And this goes back to what I mean when I say evidence. It's that which you would expect to see if your model or your theory, your hypothesis, your ideal, what have you, is true. And if inflation were true, there's a variety of things we should expect to see in our universe. And we see all of them, except one. There's only one that we haven't at least yet seen.
There's at least one what that we haven't seen? There's
as far as I know, at least one observation that that inflationary cosmology predicts, specifically inflation that we haven't seen yet, and that's the gravitational waves in the cosmic microwave background.
Okay. Well, again, Leo, what I'm saying is that extraordinary claims, and I think the Big Bang Theory is an extraordinary claim. And so I need extraordinary evidence for that. And you've provided me cosmic background radiation, which I think can have other explanations. Okay.
Such
so
as
radiation in the universe.
Such as
radiation in the universe.
Yeah.
There's many structures in the universe that are producing radiation.
Yeah, but I already addressed that, didn't
exactly
I? When I said that they can't reproduce a radiation that's uniform and homogeneous to 1 part in 100,000, that's almost nearly scale invariant. So you keep missing that. Sure, I've already agreed that there are other sources in the universe that can produce this radiation, but they can't produce a radiation that looks like this, that has this structure. And you have not yet given me something that's even remotely possible to do so. But I have a model that does.
I don't know. Can't I say I don't know?
Yeah, you could say you don't know.
So I said, okay, I agree that cosmic background radiation can be support for your model. It could also be something else. Is there anything?
Well, it could be, but I'm myself and anybody else that likes cosmology or is in the field is going to say, well, what though?
Well, I mean, I don't know.
All right, so then why not accept the model that we have, given that it seems to provide a meaningful account of what we observe?
And I've given you reasons, because the model has too many problems.
Like what?
And we've already been through this. It can't sustain itself.
Why not?
On its own, without making up a bunch of crap.
Like what?
So we already been through this, Leo.
Like, well, I don't remember
dark
going
matter,
through that. Dark energy, I explained that. I explained that. I explained all those things. I explained how they're not just things. Didn't. Yes, I did. Would you like me to do it again?
No, you.
Well, what do you mean by story?
What I mean is you're not telling me how we've observed dark matter.
Yes, I did.
You're not telling.
Can you tell me the two things that I said? Can you tell me what the two things that I said were?
The gravity. You said the gravity doesn't make sense in the spiral galaxies as we see them, and you say the way the light bends doesn't make sense.
Okay, yeah. So I gave you two pieces of evidence for dark matter. Okay. Number one, that galaxies should be flying apart, but they're not. Number two, that they curve light more than they should, given the amount of mass that's in them. And then I even asked you, what's the thing? So we know there's more gravity in galaxies than what we can see with the matter that's there. That's the normal matter that we can see. And I asked you, what's something that you think can cause gravity? Is there anything that you know of that can cause gravity? And you said, yeah, mass. And I said, okay, great. So like matter. So there could be like a type of matter there that doesn't interact with light, that's giving rise to this extra gravity, that's causing us to observe these effects of there being extra gravity from something that we can't see. And you seem to say, okay, that kind of makes sense. Instead, then you're sitting here telling me, oh, but you haven't given any evidence for dark matter, when I explicitly gave two that you seem to agree with.
No, because the only reason the problem is with the spiral galaxies is because you need the spiral galaxies in the time period that you think that they've been around to in order to sustain your model, right?
No.
I have no problem with a spiral galaxy with no dark matter.
Yeah, but the dark matter doesn't really matter for like the hot Big Bang.
But this is circular because you
no, it's not.
Want it for your What do you mean the dark matter is not?
Dark
what
matter
you mean
doesn't
by that.
matter. Like the idea that the universe was very early in its history in a very hot and very dense state could be true even if we didn't have this whole dark matter thing. You can get rid of dark matter. That would still be true about the universe. And we would still know it because of the universe that we see.
But
You
wouldn't be
just
able to
haven't given me.
explain
I wouldn't be able to explain what.
galaxies.
What about them?
You wouldn't be able to explain their formation, which you can't anyway.
We still
but
can't explain their formation even
exactly.
now. Most cosmologists are going to tell you that.
Exactly.
What does that matter?
Okay, well, because
We
if
still
you're-
don't fully understand how lightning forms. Does that mean that like Zeus is real or something like
no,
that?
but if it doesn't work within your model, then you have to question your model. But
Not
you're willing
necessarily.
are you willing to question this model? Are you willing to say that
No.
So you are not willing to say it's possible that the universe did not start with the Big Bang.
I don't think that it's nomologically possible, no, because we already know that it did. It would be like asking, is it possible that you didn't already wake up today? Well, no, because I already woke up today. Like, I don't know what else you want me to say. Like, you can't ask me if it's possible that a thing that already happened didn't already happen, even though it already happened. No, it's not possible because it already happened. So that's.
But you're assuming. You are
No.
assuming the Big
I'm not
Bang.
assuming anything. I'm concluding that the universe originated in a very hot and very dense state from the amount of data that we have with respect to what kind of universe we see.
And
If that were true, let's go ahead.
If the observations continue to mount against this model, at what point would you be willing to say the model's wrong?
Well, I wouldn't, because we know that it's not, and there isn't any evidence mounting against the hot Big Bang model. There is evidence coming in that's helping us refine the broader lambda CDM model, but there isn't any evidence coming in that confounds it in any way that would call it into question. And that's just not going to, no cosmologist is going to expect that because of the evidence that already exists that I've outlined.
All right. Well, I'm willing to leave it at that, because I feel like at this point we're arguing about the facts, right? And I've listed my references. Anybody can check them out. You can see what the problems are, and so if you want to list your references, Leo, I'd be happy to put them in the description. But I mean, now we're just arguing about the facts, because I think there is lots of evidence that has mounted against the Big Bang, and every time there's just a new thing that's created to save it. But those hypothetical entities are not backed up by observation. And so, but you apparently disagree with that. So
yeah, but it's not just that I disagree. I've shown how it's actually false. It's empirically false that they don't align with observation. I've outlined the observations, and thus far you haven't disagreed with them. You've just said that, well, but there could be some other way to explain it. And I'm like, yeah, because you're right, there could. But then you don't explain it, and then somehow say that that means that the explanation we have now is wrong.
Well, I've given you the information about the galaxies, the problem with seeing too many galaxies in the early universe where there aren't even supposed to be any galaxies.
But these aren't problems for the Big Bang. These are these are problems for our models of galactic formation. How is it a problem for the Big Bang model?
Because
no, it's not.
The Big Bang has to be able to produce everything that we see in our universe.
Yes.
Now, right?
There's a tangential relationship between how the universe evolves in time and the formation of structure within it, obviously. But the fact that the universe evolved some way isn't going to be confounded by us being kind of wrong about some really, really specified things about how certain very specified structures formed, because we just really don't have a lot of information. And you keep trying to make that inference, and that's just not going to work. No cosmologist is going to would sit here and say to you that, oh yeah, we know how galaxies form. They're going to say, yeah, we don't fully understand how galaxies form. There's a lot of information that we're still collecting, and there are certain inferences. Are you telling me there's never been an inference you've made? You saw something, you heard something, and you made an inference, and then it turned out that the inference was wrong. But it wasn't bad. It wasn't like bad to have made the inference that you did, though, right?
Right. Absolutely.
That's how this is. We have limited data. We make some inferences about how galaxies might form, what they might look like, when their formation started, and then we collect data that shows, oh well, some of those inferences weren't quite right. Maybe it was a little earlier than you thought. I don't see how that means, oh, everything's wrong and we got to throw it all out the window.
Well, I think because we're starting at different points. You're starting with the idea that the Big Bang model is correct, and I'm starting with the idea that, wow, this is a really crazy story. Like, seriously, like,
I still don't know what you mean by story.
Just our sun. Think about our sun warming this entire planet, and then billions, trillions, and even galaxies composed of those. And we're talking about all of those being in this teeny tiny speck of space. And I'm sorry, but grown-ups believe this? Grown-ups believe this. Like, grown-ups believe.
Well, but this is just kind of an argument from incredulity, right? Like, oh, you're just saying that it's kind of,
things that are worthy of being incredulous about.
Yeah, but you're just saying that you don't understand it, so it's wrong.
You should have a problem with this. This is ridiculous. Like, seriously, this is what you believe.
That's what most people believe, yes, because we have evidence to show it.
And that's what you're resting on. The fact that a lot of people believe.
No, that's not what I'm resting on. I'm resting on all the evidence that I've outlined in this discussion. Well, it is. I've outlined how. But you're just, all you made there was just an argument from incredulity. Well, I don't really understand this, so it must be wrong. Well, that doesn't, no, that's not how it works. You not understanding this, I don't know how. I think I've done a pretty good job of explaining these things. As pompous as that may sound, I think I have. But you not understanding them doesn't somehow make an idea wrong. It just means that you don't understand it.
Okay. Well, do you have any final? We can take some comments from the.
I'm okay with that. Yeah.
Do you see any? I mean, if you guys have anything that you want to put in, I started a few comments, but I think I read most of them. Okay, Cameron says this, and it's a little bit off topic, but even if everything Leo said is wrong, how does that in any way prove the Bible being God's word or Christianity is true? It doesn't. So I'm not trying to do that in this conversation, nor am I trying to do that on this channel at all. I'm not trying to prove to anyone that Christianity is true. No, I have no interest in doing that. I believe it's true, and I want people to know about it, and I want people to understand the beauty of God and the Christian faith. But I'm not trying to prove it to anyone. It's a story. And it's, I believe it's historical, but it's not something that I can prove to be true. So not trying to do that. But I do hope that in this conversation that I have caused some skepticism in people. And from the comments, it doesn't look like I have. And frankly, that is astounding to me. Like, people are just in here saying, like, Rebecca doesn't know what she's talking about, blah, 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 blah. Okay, fine, guys, that's fine. If this is the story that you've accepted and you're willing to believe it based on the,
you still haven't told us what you mean by story.
Flimsy evidence. Well, I think I did, Leo. I tried to describe it.
I also don't think that you've really shown how the evidence is flimsy. You've just kind of shown how you don't really understand it, and you don't really like the fact that it kind of shows that the preconceived notions that you've convinced yourself of. Because, I mean, let's be real here. You only reject the Big Bang not because there's no evidence for it, but because it disagrees with preconceived biases that you won't abandon, like that the Earth and the universe are 6,000 years old. If you didn't have those, this wouldn't be a problem for you. And that's why, like most Christians, because they're not young Earth creationists, don't care whether the Big Bang is true or not, because it doesn't matter to their faith. Something like that isn't that tedious because they don't have these really, really rather just unnecessary and entirely superfluous preconceptions with respect to their religious beliefs, like that the Earth and the whole universe is only 6,000 years old and was created in 6 days directly by God, which has got a myriad of issues. But that's why you're rejecting everything that I'm saying. It's not because I didn't provide the evidence. I did. I think most people in the chat, even people who may disagree with me, would say, oh yeah, he presented lines of evidence and he named them.
Okay. Well, then, I mean, Leo, while it is, I will say this, if I didn't believe what I believe about God and about the age of the Earth and everything, I would never spend a second looking into or thinking about the Big Bang. And you're right. I would probably just believe it because that's what the experts are saying. Okay. So it is because of my belief, my religious beliefs, that I looked into this. But the reason I'm willing to have a discussion about it is because as I looked into it, I was like, dang, people are believing this model based on this like little bit of support, like tiny bit of support and a
All the
bunch of
support?
failed predictions. And a bunch of failed predictions, a bunch of problems.
There's no failed.
And
What predictions does the model make that have
oh
failed?
my goodness. We already talked through some of these things, and I'm actually getting pretty tired right now because it's like 2 hours. So, but I can mention a few things again if you want.
Sure.
But you know, we have the problem of different expansion rates. We have the problem of the dwarf galaxies. We have the problem of large structures, which were not predicted in the Big Bang. Okay,
What?
and
Wait.
the universe is not as homogeneous as it should be according to the Big Bang model. But look, I don't have energy to get into another 30-minute conversation.
Well, no, I'm just saying that I addressed all of those.
There's the problem of no collisions, right? Or a few collisions, okay, of galaxies, because and what you did to explain that is, oh, well, see, that doesn't belong to the Big Bang. We can just give that to the galaxy formation problem. Well, it is part of the Big Bang, and the Big Bang needs to account for it. So that is that's a problem. There was a prediction there that was made according to the Big Bang model that we would look out and we would see collisions of galaxies, which would produce bigger galaxies and allow them to get to the size that they are. And we also predicted that there wouldn't be any galaxies out at that period of the universe forming. So we have these mature galaxies that are out there that, and some of them are, they have mature star formation, just like the Milky Way, right? But they're like out at 330 million years after the Big Bang. So not only do you have to explain why they are there at 330 million years, but how did they get to that star forming period if they're not older than the Big Bang itself? That good luck. I mean, so there's tons of failed predictions and tons of problems here.
Yeah, so I already addressed literally every one of those with respect to the differences in the measurements of the expansion rate of space-time. There is a tension there. It's not like cosmologists like scream whoa about it, but it's largely kind of like a troll. It's really not like that big of an issue. It does not defeat the fact that we know that the universe is expanding and that it's accelerating in its expansion. After all, these two measurements that disagree with each other are measurements of the expansion rate. So obviously the universe is still expanding and it's accelerating in its expansion. And we're just not sure about, we just don't have an accurate measurement of what that rate is. With respect to the galaxy stuff, dwarf galaxies, galaxy formation, galaxy size, these just don't matter because these are only very tangentially related to the Big Bang model. And cosmologists fully admitted that most of their models with respect to galaxy formation are probably largely incorrect because we don't have a lot of information about that. The James Webb Space Telescope is revealing a lot more information, and we are revising those models. So these are either A, predictions that aren't made. That's really what it is. None of those were predictions made by the hot Big Bang model.
Okay, well, thank you, Leo, for taking the time today. And I have to say, you did a fine job defending this theory as best as anyone could do, I think. And so thank you for being willing to do that. And
thanks for having me on.
For those who are watching, please do subscribe to Leophilius. The link to his channel and his Twitter page is in the description of this video. And he does great talks on science and philosophy. And I think you're going to be doing a weekly join and talk live stream. Is that right?
I think I'm going to do it bi-weekly just because I think that way it doesn't sit run out of steam more quickly. But yeah. Those are going to be on
Okay.
Thursdays.
Awesome. Well, thank you everyone for being here. Thanks for listening to this conversation. Hope everyone has a happy new year.
Can I give a
And,
shout out to two people
yeah.
in the chat?
Sure.
I want to give a shout out to Rebecca's #1 chatmate, Sal Cordova, Evidence and Reasons out there. How you doing, buddy? And then I want to give a shout out to Andrew Cumming, my #1 chatmate, because he was out there on my side. So I just wanted to give a shout out to those two in the chat.
Wait, who was the other chat mate that you wanted to shout out to besides Sal?
Andrew Cumming.
Andrew Cumming. Is he there anymore? Because I haven't seen it. Oh, wait. Yeah. Here he is. Okay. Hey, Andrew. Okay. And yeah, we can say hi to Top Dog, YouTube Punk, Excuse Me But, Captive Dusk, Jerome, BS Lewis, Rebel Nazarene, Satan, Gorgeous Roddy Chrome, Luca. Wow, we had a lot of people here today. Jamie Russell. Thank you guys for being here and have a great night and Happy New Year.